In this video, we will learn about oxidation and reduction chemistry revolving around carbonyl-containing functional groups. What we're mostly interested in is how to create carbonyls from alcohols and how to turn carbonyl-containing functional groups back into alcohols. And so when we're talking about reduction and oxidation, there are two different types of definitions that you will have to become familiar with. The first one is the one that's learned in general chemistry usually, which is the one that deals with the oxidation or redox state of a metal ion. So for example, copper 2. In organic chemistry, the definition revolves around the number of heteroatom bonds to a given carbon atom. And because of that definition, what we see is that we can relate different oxidation levels actually by a change in either plus or minus a molecule of H2. Let me show you what that looks like in two reactions here. So here is an alcohol oxidation. I'm using this bracket O as a generic we're oxidizing reaction condition. What you see here is that this carbon right now goes from having one bond to oxygen to now having two in the product, and it has lost a hydrogen, and the oxygen has also lost a hydrogen, and so that means overall we're losing those two hydrogens and one pair of electrons. You can see the same thing in a reduction reaction. So here I'm using the bracket H to indicate a generic reduction reaction. So for an ester, here I'm showing you a reduction that happens twice. Say twice because we go from having a carbon with 3 bonds to heteroatoms to only having 1 bond to a heteroatom. And so here what we're doing is we're essentially adding 2 molecules of H2 to the molecule. So again, for organic chemists, when we're talking about organic molecules, our frame of reference is the change in the equivalence of H2 being added or removed from a molecule. So let's start off looking at reductions. The way a reduction works is it's essentially a two-part process. The first step is a carbonyl addition reaction in which a hydride is the nucleophile. The second part is the protonation that happens usually in the workup step. And so what that means is that it looks like this. We get a plus, an H minus, and a plus and H plus. If you add H minus and H plus together, you get to a molecule of H2. So that's why we think in terms of equivalence of hydrogen gas. So for these reductions, there's a couple different variations we want to know about. The first one is that borohydrides are useful for reducing ketones and aldehydes, but are generally not reactive on more substituted carbonyls. So, for example, esters and amides. So here's an example of reduction of the molecule acetone with sodium borohydride to isopropanol. Here's the mechanism for the reaction. This is just a typical nucleophilic addition to a carbonyl, but I'll go ahead and draw it out anyway. So what we're having is the sigma nucleophile of a borohydride that is attacking in here, getting us to the tetrahedral intermediate. This tetrahedral intermediate doesn't have a leaving group on it, so it stays as is. And finally, during either a workup step, or in this case I have a protic solvent, then I can do the acid-base reaction to get to the alcohol product. If we want the arrow pushing, then that looks like this. So again, the functional groups such as esters and amides, which are less electrophilic than ketones and aldehydes, those will not be reactive with borohydrates. So here's an example of that. And again, the reason is that this is a less electrophilic carbonyl. And so you can imagine that there are cases where we want to be able to reduce esters and amides down into lower oxidation level functional groups. And in order to do that, we are dealing with a less electrophilic electrophile, so we need a stronger hydride nucleophile. And that's exactly what people did. So historically, people came up with the idea of, instead of using borohydrides, to use aluminum hydrides, so one row down in the periodic table. That's enough to increase the reactivity of the hydride to enable it to react with esters and amides. So the first most common reagent is this one, lithium aluminum hydride, or LAH. This is considered a very strong reducing agent. So an example of this reaction here would be this molecule that's both got a ketone and an ester in it. Reacting with lithium aluminum hydride gets you reduced all the way down to the alcohol in both of those carbonyls. So it's worth our time to go through the mechanism here. So we'll do that. You start off with a nucleophilic addition of hydride to the carbonyl of the ester, and what we're going to do is actually show it directly then breaking the pi bond and having that pair of pi electrons just pick up the lithium cation to form an oxygen-lithium bond here. It turns out that if you study these types of intermediates in general, what we find is that lithium cation tends to bind very strongly to oxygen in a way that's much more like a covalent bond. So this is representing either oxygen minus lithium plus or just oxygen lithium bond. Once you're here, then what we have is a tetrahedral intermediate. This tetrahedral intermediate does have negative charge on oxygen, and it does have a leaving group attached, and so we should expect a collapse or an elimination to take place, getting us to now this species, where I have gone ahead and combined my salt together, and I have an aldehyde. And so if you think about the electrophilicity of an aldehyde versus an ester, well, aldehydes are much more electrophilic than esters, and so as soon as any aldehyde is made by this first process, we should expect that the next time that lithium aluminum hydride is floating around and collides with an aldehyde, it will immediately reduce in preference to the ester. So then we would do that reduction again, do our attack, pick up the lithium, get to another tetrahedral intermediate, this time with no potential leaving groups on the tetrahedral intermediate. And so this is the theoretical resting point, except for the possibility of potentially reacting with the aluminum byproduct here. So we can also get to forming the aluminum hydride that is kind of including our product. Whatever the resting point is, it's either going to be here or some analogous compound to this one. Until we do the protonation step in the workup, we won't get to our final product. And so that step 2 is when I, as the experimentalist, go in and add an aqueous solution of NH4Cl, which is essentially NH3 and HCl, so it's a mild acid source. And this goes ahead and protonates and gets me my alcohol and a bunch of aluminum waste. So if you ever have to run one of these reactions, dealing with the aluminum waste is actually the hard part of this reaction. And so naturally you should ask the question, well, if LAH is such a strong reducing agent and brings everything down to alcohols, aren't there going to be times where we want to take an ester and turn it just into an aldehyde and stop there? And the answer is yes, there definitely are times where you want to do that. And there is a solution. So since our nucleophile LAH is too strong, the solution is to come up with a version that is just less nucleophilic. And so the version that was come up with is called diisobutyl aluminum hydride, or dibal, and it looks like this right here, where this attachment of the 4-carbon group here to aluminum, this 4-carbon group is called isobutyl group. And what you can see right away is that this is a neutral aluminum versus the negatively charged aluminum that we have in LAH. And so the way we think about this is that LAH is a nucleophilic reducing agent, while dibal is an electrophilic reducing agent, and it's electrophilic because the aluminum has less than a full octet. And so here's an example of that reaction in action. So ester, we do dibal. We're running this at negative 78 degrees, which is a very common temperature for organic reactions because that's what you get when you combine dry ice with acetone. The purpose of the temperature is to just keep everything very stable. We'll come back to that in a second. So let's look at the mechanism. Since dibal is an electrophilic reagent, what we're going to expect is that it's going to be an electrophile first. It does not have a nucleophilic hydride right now. And what that looks like then is actually like this. So if I have my carbonyl, what I'm getting is an addition that looks like so. You could imagine that this entire dibal is essentially just a big proton, and that would kind of look like an acid-base reaction. Right? So just the lone pair reacting with an electrophile, creating a sigma bond. After that, what that does is then that causes the aluminum to gain a formal charge, and so now this then causes the hydride that's attached to be nucleophilic. Once that's nucleophilic, we can get that nucleophilic attack there onto the carbonyl and the breaking of the pi bond, getting us to a tetrahedral intermediate. This process regenerates a neutral aluminum species here, and we have this tetrahedral intermediate that, because it's so neutral overall, is not very prone to collapsing. So this is stable at low temperatures, such as minus 78 degrees Celsius. Part of it is that the charge here is so nicely balanced. We don't get formal charge on oxygen as much as we do in the case up here where there's a more polarized bond. So this is just less liable to collapse in the first place. And the other part of it is just we're just so cold we can't even get over whatever activation energy barrier there is to that collapse. And so that's the resting point of the reaction. And we hope that because each aluminum here has exactly one hydride nucleophile on it, we can control exactly how many are going to react. So if I have one ester, I put in 1 molar equivalent of dibol. Once the reaction is done, then I go in and add my workup step. And so I perform the workup, I protonate here. Essentially, whenever we do the workup, we're swapping out the metals and putting in a proton. And that creates a hemiacetal, which we should recognize will equilibrate back to the aldehyde. And so again here we have a really nice example of two very similar reagents, but a slight tweak causes one of them to be much more reactive and the other one to be less reactive. And the trick in being less reactive was to control the stability of the tetrahedral intermediate and prevent the formation of a more electrophilic aldehyde in the reaction mixture. Those are reduction reactions. There's of course many other types of hydride sources, but they're all going to function relatively similarly. Now let's look at oxidation reactions. So the generic scheme for an oxidation involving carbonyls will look like this. We can oxidize from an alcohol into a ketone or an aldehyde, and we want to be a little bit careful because only aldehydes can then be oxidized into carboxylic acids conventionally. The reason for this is because alcohols can only be oxidized once per CH bond when we're thinking about the carbon attached to the alcohol oxygen. And so what we then find out is that if you look at the primary alcohols, they have 2 CHs right here. And so they are able to therefore undergo 2 oxidations to get to carboxylic acid. A secondary alcohol has only 1 CH. So it can be oxidized one time into a ketone. And finally, a tertiary alcohol has no CHs here, so it can't be oxidized at all. So these will just stay as is during any of these oxidation reactions we'll talk about. The general scheme of a carbonyl oxidation, or maybe an alcohol oxidation if you want to think about it that way, is to put a leaving group onto the oxygen and then perform a beta elimination reaction. And we need to perform this beta elimination step because we need to create a pi bond. And what we need to do in doing all this is we need to remove 1 hydrogen from the carbon and 1 hydrogen from the oxygen. And it turns out, chemically speaking, for organic chemists, it's easier to deprotonate one of these CHs here and have a leaving group installed on oxygen. What that looks like is like so, where we are somehow putting on this leaving group onto oxygen, then we're performing a beta elimination that gets us to the new carbon-oxygen pi bond. Let's go over some of the common types of oxidation reactions that are used in the lab. The first one is the hypohalide acid reaction condition, and these will oxidize our alcohols up as much as possible, so from primary alcohol all the way to carboxylic acid. So I have an example of such a reaction here where I'm showing you a diol molecule. The notation here where I have a parentheses and 8 around it indicate that there's a CH2 here repeated 8 times in a row. So you can imagine this is just a very long molecule, a very long chain, and it's just too annoying to draw out, so we often just simplify like so. The reaction conditions look like this. We use excess of NaOCl. This is actually just regular bleach, so if you're ever bleaching anything, this is what you're using. And we run the reaction in some acid, in this case acetic acid, often abbreviated ACOH, and that's the structure right there in case you're interested. After this reaction, we oxidize all of our alcohols up, get to all of these carboxylic acids and ketones. The mechanism for this reaction has a few different phases to it. So you'll notice in my reaction conditions I didn't put 1 and 2. So this 1 and 2 I'm drawing my mechanism are not indicating the 1 and 2 in the reaction as separate experimental steps. These are just indicating that there's separate phases within a single reaction flask that are kind of taking place. So the first thing that needs to happen is we need to actually form the active oxidant. And it turns out that bleach is not the active oxidant for this reaction. What we're doing is we're going to actually go and protonate the bleach here with the acetic acid to get us to this compound, which is called hypochlorous acid. This is a weak acid with pKa of only 7.5. The second thing that we observe is that a second acid-base reaction can actually happen where we protonate again and get to the protonated hypochlorous acid, and this is our actual oxidizing species. So when we think about the oxidation reaction, it goes like this. So we have our alcohol. We're reacting with the oxidizing species here. This species is electrophilic on chlorine because we have a water molecule as a leaving group. This creates a new oxygen-chlorine bond, and you can imagine that this equilibrium should be pretty much K equals 1 because you have essentially the same thing on both sides, right? You have a chlorine-oxygen bond over here, you recreate a chlorine-oxygen bond, not much else has changed in energy. Once you get to this state, we can first do the acid-base reaction to get to our neutral compound, and now we're exactly where we need to be, which is to have the leaving group attached to the oxygen, and to have our CHs ready to be deprotonated. So the conjugate base of our acetic acid comes in, so that's our acetate, comes in, deprotonates, performs beta elimination, and a chloride ion can leave. That gets us to the aldehyde here. If you're looking at these individual steps and wondering what's going on, this first one is actually called an SN2 mechanism. What's happening is the nucleophilic pair of electrons on oxygen is attacking the sigma star that's coming from the oxygen-chlorine bond here. So this is a sigma star electrophile. Because we're attacking the sigma antibonding orbital, we therefore break the sigma bond that it's associated with. And that's an SN2 mechanism that's covered later on in the class. The next step is the acid-base reaction, and then finally, of course, we have our beta elimination to make the carbonyl. The issue that we have is that we don't stop at the aldehyde because we have water in our reaction, we have acid in our reaction. That acid will catalyze the formation of aldehyde hydrate. This hydrate now just looks like an alcohol. So the exact same sequence of reactions here can happen to the aldehyde hydrate, which then results in the creation of a new carbonyl by elimination, and thus getting you to a carboxylic acid. This is a good place to practice and see if you can apply this concept to the second step of the oxidation. A second class of reagents that was historically much more popular but have fallen out of favor more recently are some that are based on chromium. The reason these have fallen out of favor is because chromium is highly toxic and a huge environmental problem. However, it's really good at the chemistry it does, so we still like to learn about it. The first version of the reaction is called Jones oxidation. This is a very, very harsh oxidation reaction, and it will oxidize everything as much as it can. So for example, if I take a benzyl alcohol here, I react it under the Jones oxidation conditions, which are like this: chromium trioxide, sulfuric acid, water, acetone, which has this structure as our solvent. Then we can make the benzoic acid very easily. So the mechanism for this reaction will be analogous to what we just looked at, in that we first have to form in situ or during the reaction a reagent or actual active species. That happens by having chromium trioxide get protonated by sulfuric acid and then be nucleophilically attacked by water, getting you overall to chromic acid. So the chemistry here is very analogous to carbonyl addition chemistry. Once you have that Jones reagent, the oxidation occurs like this. Again, we have our alcohol. What we're trying to do in these oxidations is to get a leaving group onto the alcohol, and to do that, we are always using an electrophilic species and having the alcohol be our nucleophile. When we're dealing with non-carbon atoms, what we're going to do is to just have our reactions look like this, where we're attacking that sigma star orbital, so kind of that SN2 type of step. Actually, if you look at this, what you see is essentially an esterification reaction. We've taken an atom double bonded to oxygen and single bonded to OH, and we've substituted away the OH and put in an overall an OR group. And so because of that, we draw the analogy, and nomenclature-wise, this is called the chromate ester. This chromate ester has the leaving group on the oxygen, and so with the two hydrogens right here on the carbon, we can then perform elimination, getting us to the aldehyde and having a chromate as our leaving group. The base that you might use for this elimination reaction can be all sorts of things. It could be the conjugate base of the sulfuric acid that is floating around. It could be water that's just the solvent, and that's probably more likely because that's present in such a large amount. Finally, the third step, we are in reaction conditions with strong acid, water, so that means that anytime we have a carbonyl, really it's going to exist a lot of the time as its hydrate form, and so the hydrate form can then be oxidized following the exact same reaction sequence to get to the carboxylic acid, if there is a CH to be oxidized. It turns out that even with these harsh chromium reagents, there are ways to reduce the reactivity in a way that allows us to stop the reaction at the aldehyde. So the way to do that is to use a reagent called PCC, which stands for pyridinium chlorochromate. Again, it only oxidizes up to ketone or aldehyde. An example of this reaction looks like so, where the PCC reagent is right here. Here we have the pyridinium. So pyridine is the six-membered ring. The pyridinium, the inium, refers to the protonated positive charge state of the molecule. And then we have a chromate, except there's a chlorine here instead of having an OH here. So it's a chlorochromate. So the way this works is that because there's no water anywhere in the reaction, there's no kind of water as a byproduct because we have a chlorine here as our leaving group on chromium rather than an OH. So then there's no way to form an aldehyde hydrate during the reaction. And so if you can't form the aldehyde hydrate, then you can't do the second oxidation step. So you can imagine that it's very, very important during this reaction to keep everything very dry and moisture free. Otherwise, you might start to get unwanted oxidations. Mechanistically, this will follow the same process as for Jones reagent. Again, a good place to practice drawing a mechanism for a somewhat new situation. The third oxidation I want to talk about is the Swern oxidation. This is a very useful reaction. It's very mild, so it works on a lot of different types of molecules. And for chemists, one important thing that this oxidation does is it actually demonstrates selectivity for primary alcohols over secondary alcohols. So a common problem you'll have is a molecule will have both a primary alcohol and a secondary alcohol in it, and you actually only want to react the primary alcohol. A Swern oxidation is kind of the go-to to try to make that happen. So the reaction looks like this. It's a three-step reaction now, where there's actually three separate parts to the reaction that you have to do. So the first thing is to take this reagent right here. This is called oxalochloride. React it with a reagent DMSO. Then, in a second step, once you deem this first part complete, you add in your alcohol that you would like to react. And then in the third step, you add in a weak amine base. So this is a triethylamine, which is a type of trialkylamine. And trialkylamines often show up in organic chemistry as weak bases. Once you do that, then you get to your aldehyde. So let's go over this mechanism. You start off with DMSO, dimethyl sulfoxide, which has this significant resonance form. What happens here is we do a carbonyl substitution. So what we have in oxalochloride is really this is two acid chlorides, and we basically go ahead and do a substitution. I'm going to do a little bit of shorthand here, where I am indicating that I have attacked the carbon of the carbonyl. I have gone up, and then I am going to just go ahead and directly collapse, all in one step, just to save myself space. When you do that, then you get to this kind of weird-looking ester-like species. What you have here is actually an ion pair, which is nucleophilic chloride, and then now an electrophilic sulfur. And so this is more electrophilic than it is in DMSO because the negative charge on oxygen is now gone, right? That formal negative charge is gone. So this is much more of an electrophilic site. So we get this nucleophilic attack of chloride onto sulfur. This actually performs a substitution, so an SN2. And I'm going to show this in a slightly strange way, which is to actually go like this. So what I've done here is I've created a oxygen to carbon double bond, and I've broken this carbon-carbon sigma bond. I've put it as a lone pair on this carbon, and then kind of at the same time, we get what looks like a tetrahedral intermediate collapse, but it's not tetrahedral because this is an sp2 carbon, so this is essentially a beta elimination of sorts. The reason I go through the trouble of showing you all that is because in the end, what you actually get looks like this. This whole thing is not very stable, so the initial attack here kind of triggers the decomposition of all of this into CO2 gas, carbon monoxide gas, and then chloride ion, leaving you finally with your oxidant, which should remind you a little bit of the hypohalide reaction conditions. Once you have that, then you can get the alcohol to do your SN2 substitution at the sulfur, and thus generate the leaving group on the oxygen atom after acid-base reaction. You'll notice that I attacked sulfur here instead of chloride. That's because overall here, the positive charge is on sulfur, so that's the more electrophilic side. At this point, then you have this species kind of sitting around in a reaction mixture, and once you decide that the reaction has reached that point and that all of your reactants have entered into this stage, once you're ready to go ahead, then you can add in the weak triethylamine base. The different thing here is that the most acidic hydrogen is actually not the one that's here that we're expecting to oxidize. The most acidic hydrogen is the one closer to the formal positive charge. So actually the methyl groups next to positively charged sulfurs have surprisingly high acidity. So those are acidic, and we get deprotonation there. And when that deprotonates, our elimination happens this way to get us to what I'm going to leave as a lone pair on the carbon. So I'm going to go ahead and draw in these hydrogens and a lone pair. This species is called an ylid. That word refers to whenever you have a lone pair negative charge and a positive charge adjacent to each other. This ylid now decomposes easily, but it does so in a different way that kind of does the whole oxidation step all at once. So the acid-base reaction now is intramolecular, so this is a little bit easier to do instead of having to wait for two molecules to collide the right way. Whenever these two molecules collide, the electrostatic attraction is bringing it to over here. Here, you don't have to wait for collision, so you can get the actual elimination you want. Then you can eliminate and do like so. That overall gets you to two new molecules. One is dimethyl sulfide, and the other is your product aldehyde. Again, if you set this up correctly, you don't have any aldehyde hydrate to further oxidize. And secondly, this reaction is often known for being very smelly because this byproduct here, dimethyl sulfide, is very, very smelly. And so successful Swern oxidations often come with what chemists will call a sweet smell of success. So that was a look at a few reduction reactions in which we take some carbonyls and bring them down to lower oxidation levels, so either to either ketone or aldehyde or all the way down to an alcohol. And also a look at some oxidation reactions where we start from either alcohols or ketones and aldehydes and go up in level, create kind of more carbon-oxygen bonds. We went over some of the mechanistic details, which are good to understand and think about conceptually in terms of why certain reactions happen certain ways. And we've expanded our toolkit of different types of reactions we might be able to use to turn a given molecule into another one.